The definition of a basis is on the screen. You look at the definition. A basis of the subspace of Rn is a collection of vectors in orders. Okay, satisfying two conditions. I want to mention the two conditions. One condition is that the vectors they span S. Okay, so very shortly I'm going to tell you what's going on using a particular subspace and a set. Okay. Again, two conditions. One condition is the given vectors they span S. So by that we mean every vector in S is a linear combination of the given vectors. So that's one of the two conditions. They span S. Okay. The second condition is that the vectors they are linearly independent. Again, two conditions. The first condition, it means every vector in S is a linear combination of the given vectors. The second condition is that the two vectors, the given vectors, are linearly independent. Okay. Now we'll use a particular question to show you the meaning. Now, for example, I'm going to write it here. Okay. For example, again, I'm talking about what we mean by a basis of a subspace of Rn. Now, for instance, R2 is a subspace. Okay, R2 is a vector space, so we have seen that before. In particular, R2 is a subspace of R2. We also mentioned that before. Okay, every Rn has two trivial subspaces, right? We mentioned before. One trivial one is itself, so the other one is the set consisting of only the zero vector. I'm trying to say R2 itself is a subspace of R2. Now I'm going to use a particular set of R2 to talk about what we mean by a basis of R2. Okay. Given R2, so maybe given R2, we are going to verify the two standard basis vectors is actually a basis of R2. Okay, and then we'll verify I consisting of two components. So now let's say 1, 0, and the J has two components. So now let's say 0, 1. We're going to verify the two conditions for these two vectors. By that we mean we're going to show these two vectors are indeed a basis of R2. The two vectors they form a basis of R2. Okay. Again, two conditions. The first one is every vector in the subspace, in particular every vector in R2 is a linear combination of I and J. We have seen that too many times, right? Two conditions. The first condition, every vector in R2 is a linear combination of I and J. So by that we mean the two vectors they do span S. Okay, I and J span S, span R2 itself. In this particular case, the subspace we are talking about now is R2 itself. Okay. The second condition we also have seen many times. The two given vectors I and J are linearly independent. Okay. We mentioned that last time, right? None of the two vectors is a linear combination of the other vector. That's one of the equivalent conditions under which the two vectors are linearly independent. Okay. So you just say I and J are linearly independent. Okay. So see the two vectors I and J satisfy the two conditions. Again, I want to repeat the two conditions. One condition is that the two vectors they span R2, and the two vectors they are linearly independent. I should have I and J are linearly independent, right? So the two conditions are both true. That's why I and J form a basis of R2. Yeah, that's why we call it I and J the standard basis vectors. Okay, it's the simplest basis vectors of R2, of course. Okay, and of course, R2 can have other basis vectors as well. Okay, but we'll move on to talk about some more complicated cases. Okay, we're going to study a subspace of R3. Okay, we'll work on the two questions one by one. Now in question A, now the solution to the question. Okay, solution to question 3. In question A, to get a basis, we want to get a collection of the vectors of S satisfying two conditions. Again, the way to get the two vectors from S is the same as before. In the set, A and B can be any real numbers, and then the third component is A plus 2B, right? We get two vectors. The first one is using A value of 1 and B value of 0. Okay. The second one is to use A value of 0 and B value of 1. Okay. In question A, we're going to find the two vectors. Okay. So we find the two vectors first. So we let A value of 0. We let A be 0, okay, and we let B be 1. So how about we use A value of 1 first? Okay. We use A value of 1 and B value of 0. And then we have a vector in S given by A value is 1 and B value is 0. And then the third component is determined by the first two components. The third component, I believe it has to be 1. Right? And we use A value of 0 and B value of 1. We have A value of 0 and B value is 1. And then the third component is 2B. I believe it's 2. It's 2. Okay. I told you how to find two vectors. And then we are going to verify two conditions in order to say the two vectors, they form a basis of S. Okay. And then you say something like, we claim. By that we mean we want to show the two vectors, they form a basis of S. We want to claim the two vectors. So can I label the two vectors using something so like U and V? I want to call the first vector U. Okay. I want to call the second vector V. And then we claim the two chosen vectors are indeed form a basis of S, the subspace. Okay. We claim. So now let's say U and V, they form a basis of S, the subspace. Okay, we have seen S is indeed a subspace of R3, right? Now we want to show U and V indeed form a basis of S. Again, two conditions. You need to verify the definitions here. I label the two conditions. You want to show the two chosen vectors, they span S. You want to show the two chosen vectors are linearly independent. Okay. After showing that, I'm going to make more comments. In fact, indeed, so however you say it. In fact, the first condition, okay, label the first condition. Now we show every vector in S is a linear combination of the two chosen vectors. Okay, we have seen that already. So by that we mean we want to show the two chosen vectors span S. Okay. For each vector in S, for each vector So now let's say the first component A, the second component B, the third component is A plus 2B. For each component in S, for each vector in S, okay, we want to show every vector in S is a linear combination of the two chosen vectors. The vector, each vector, now let's say with the first component of A, the second component B, the third component A plus 2B is a linear combination of U and V as, so now let's say A times U, right, and then plus B times V. You can verify easily, right? Actually, we have seen that many times. What is the meaning of that? Each vector in S is a linear combination of U and V. After this, you can conclude the two vectors they span S, right? That's the definition of a spanning set. You say something like so. The two vectors they span S, U and V span S. Okay. One more condition. The other condition to show U and V form a basis. The other condition is we have to show the two vectors U and V are linearly independent. So by that we mean these two vectors, none of the two vectors are redundant. Actually, no vector of U and V is a linear combination of the other vector. Okay. Now we want to show the two vectors are linearly independent. Secondly, now let's recall the shortcut method. Okay, the shortcut method we mentioned last time. How to determine if a collection of vectors are linearly independent. How can we do that? Let's recall the shortcut method. Okay, to determine if a set of the vectors are linearly dependent or independent, we form a matrix, right? Form a matrix with the components of U and V in columns. By that I mean the components of U 1, 0, 1 go to the first column. The components of V 0, 1, 2 go to the second column, 0, 1, 2. Okay. This one is simple. By that I mean I'm trying to say it's easy to put the matrix into RREF. After getting the final form in RREF, we can determine if the given vectors are linearly dependent or independent. Okay. Now we perform elementary row operations. Actually, you do not need too many steps. I will skip that. Okay. I believe you are going to have a matrix in the form of 1, 1, 0, 0, and then 0, 1, 0, 1, 0, the second column. Now check your notes. Now my question is, are the two vectors U and V linearly dependent or independent? You check the columns. Now let's recall the shortcut method we did last time. Now you check the columns. If every column has a leading 1, then the given vectors are linearly independent. Okay, so the given two vectors U and V are linearly independent. Now you see the two conditions are both true, right? Are satisfied. The first condition is that U and V form a spanning set. By that we mean every vector in S is a linear combination of U and V. It means U and V they span S, the subspace. Okay. The second condition is that they are linearly independent. So the two conditions are both true, satisfied. Okay, and then we can conclude the two vectors they indeed form a basis of S. Okay. So they form I will read the full sentence. Okay, to conclusion. To draw the conclusion, I'd better use the full sentence, and then you'll say something like, so the two vectors u and v indeed form a basis. U and v, I mean, okay, a basis of S. Now you look at question A. In question A, I showed you how to find a basis. To justify, I mean, you need to verify the two conditions. We have seen the two conditions are both true, right? Okay, and then we can find a basis. Again, by justifying, we mean you verify the two conditions. Okay. And then in question B, I haven't told you the definition yet. Okay. So before that, I'm going to make more comments. By linearly independent, we mean none of the two. So first of all, the two vectors they span S, and then the second condition it means none of the two vectors is redundant. By that we mean if you remove any of the two vectors, they cannot span S. Okay. Now I want to mention the dimension. I will include the definition of the dimension on this screen. After getting a basis of S, and then we can determine the dimension of the subspace. Okay. Now the definition again. The definition is part of the definition on top, actually. Okay. The definition. The number of, so copy it down. Okay. The number of basis vectors is called the dimension. We're talking about the dimension of a subspace. The number of basis vectors in any basis is called the dimension. So denoted by, there's a notation, a standard notation for the dimension of the subspace S. It's denoted using that notation. DIM for dimension. Okay, it's called the dimension of S. Simple. Okay. Now let's go back to the question we are doing right now. Now we are working on question B. You look at the question B. Okay. In question B, we're trying to get the dimension. Again, by dimension, it means nothing but how many basis vectors in any basis. In question A, we found a basis, right? We proved U and V form a basis. And then you just count how many vectors in the basis. 2 vectors in the basis. So the dimension is 2. Okay. Now for question B. According to question A, we have seen the dimension of S is equal to 2. So because in the basis you have 2 vectors. Okay. Actually, it can be proved. Actually, the basis may not be unique. It's possible to get 2 other vectors to form the basis. It can be proved in any basis. They have the same number of the basis vectors in any basis. Okay. By that we mean no matter which basis you use, the dimension is always 2. Okay. a little bit more common than that. So probably we have seen the geometric meaning last time on the quiz. Okay. So because you have two vectors which are linearly independent, it means none of the two vectors is a linear combination of the other one, no redundant ones. Okay. Now we try to see the geometric meaning of S. We mentioned that last time, right? Now we check the geometric meaning of S. You have two vectors, u and v. So in this particular case, I don't know where these u and v are, but it's possible to make u and v more precise in the diagram. But I'm showing you the meaning. Okay, you have two vectors u and v. Linearly independent. It means none of the two vectors is a linear combination of the other one. In this particular case, it means the two vectors are not parallel. The two vectors are not on the same line. Okay. Can I say that way? The two vectors are not parallel. Now let's understand the meaning of S. The spanning set, the two vectors, they span S, and it means every vector is a linear combination of the two vectors. Okay. You imagine all possible linear combinations of u and v. They form a plane passing through the origin. Okay. Okay. Again, they are linearly independent. It means none of the two vectors is a linear combination of the other one. Okay. The two vectors are not on the same line. So that makes sense. S is actually a plane passing through the origin. That's why the dimension is 2. That's why the dimension is 2, okay? A plane is a two-dimensional stuff, right? Okay, basis, it means there are two vectors can span S. And also the two vectors, none of the two vectors is redundant. So these are the two meanings of the two conditions. Again, I want you to use the particular case to understand the dimension is 2, and you need two vectors to span S. Okay. In particular, I want you to see the geometric meaning of S as a plane passing through the origin. So just some more comments on question A and question B. And for question C, I'm going to do it a little quicker. Okay. My intention on question C is to show you it's possible for a subspace to have a different basis. Now we are trying to show these two vectors also form a basis. So first of all, we answer question C. So the answer is yes. And then we verify the two conditions. Okay. We say something like, so yes, maybe in fact, two conditions for a basis of a subspace. The first condition is every vector in S is a linear combination of these two vectors. Okay. Should I introduce some new notations? I don't think it's necessary. I'll try not to introduce new notations, UB and so on. Okay. In fact, so we want to show each vector in S is a linear combination of these two vectors. We choose an arbitrary vector from S. Okay. For each vector AB, A plus 2B, every vector in S has that form. In S, we want to show each vector is a linear combination of the two vectors in question C. Okay. For each vector in S, we have each vector in S, AB and then A plus 2B. We want to show it's a linear combination of the two vectors in C. So by that we mean we want to write each vector in S as a linear combination of the two vectors. 2, 0, 2. The second vector is 0, 2, 4. Probably we have seen that many times already too. Okay. The two coefficients, the two numbers, the two coefficients, the two scalars you can choose are numbers like you verify. Okay. The first number is a over 2. The second number is b over 2. We have seen that many times, probably. Okay. This shows each vector in S is a linear combination of the two vectors in question C. So the two vectors in question C, I mean they span S. They span S. Again, it means every vector in S is a linear combination of the two vectors in S. I mean every vector in S is a linear combination of the two vectors in question C. That's the first condition we need to verify. Now the second condition, okay? The second condition is very similar. We want to show these two vectors. None of the two vectors is redundant. It's the least number of the vectors spanning S. By that we mean we want to show the two vectors are linearly independent. Okay. The same as before, to show two vectors are linearly independent, we form the shortcut method. Okay, we use the shortcut method. We form a matrix with the components of the vectors in columns. The first column 2, 0, 2, the second column 0, 2, 4. And then we perform elementary row operations to put the matrix into RREF. I will skip that. Okay. I think you can do that easily in this particular case. The final form is actually the same as before. First column 1, 0, 0. The second column 0, 1, 0. Again, I kind of lost my voice actually. Again, I'm trying to say, recall the conditions under which the two given vectors are linearly independent. You check the column. Okay, you check the columns. Every column in the final form has a leading 1. That's the condition that the given vectors are linearly independent. Okay. The given vectors, I will call them they. Okay. So they are linearly independent. I mean independent. Okay. The two conditions are both true, are satisfied. Now you can conclude. So maybe I will change a connection word. Therefore, the given vectors in question C, I mean the final sentence, I'm going to write the full sentence. The given two vectors 2, 0, 2 and 0, 2, 0, 2, 4, they indeed form a basis of S. So do not just say they form a basis. You have to say they form a basis of which subspace. In this case, we want to say they form a basis of the subspace of S. So that makes sense? Again, my intention on question C is to show you the basis of a subspace is not unique. It's possible for a subspace to have a different basis. But it can be proved any basis of a subspace have the same number of the vectors. So we can talk about the dimension of the subspace. Right. Any questions? A question like that will be on Friday's quiz, of course. And then we talk about, we move on to part 6. Actually, I wanted to do question 4 earlier, but we'll see. The questions in part 6 are more important. I will move on to part 6. Okay. In part 6, it's kind of the summary of all the properties of subspaces, bases, spanning set, and many things. It combines many things, okay, into one question. Okay, now we'll work on question 2 first.
So can you show me the previous solution, please?
Okay, sure. So this one?
Yes.
Okay, sure.
Thank you.
Okay, no problem.
Yeah, it's done. Thank you.
Okay, sure, thank you. Okay, now we move on to part 6. We'll do question 2 first. On the final, there will be a long question, so something like this. Okay, for a collection of vectors in R3, I'm going to ask you all the questions on the final exam. Of course, on the final, you are going to have a different set of vectors. Probably I do not have enough space to copy all the questions. Okay. But we're going to answer all the questions. Try to remember question A. In question A, we're trying to determine if the given vectors are linearly dependent or independent. Okay. If they are linearly dependent, I want you to write one vector as a linear combination of other vectors. Okay. So maybe I will just copy question A to this PowerPoint. On this slide, we concentrate on question A. Okay. Again, we use the shortcut method. Okay, it's much easier, but in most cases you do not see why, but it's easier to do questions. Okay, if I do not specify what method you have to use, you can use the shortcut method. Now for question A, we form a matrix with the components of the vectors in columns. Okay. In order it's easier to communicate, I'm going to call the first vector U. I will call the second vector V. Okay. The third vector W. So I do not have to write all the components in many cases. Okay. For question A, again we form a matrix with the columns of U, V, and W in columns. The first column has 1, 0, 0. The second column has 0, 1, 0. The third column has 2, 3, 0. Right. And then our target is to make the matrix REF. It's already in REF, right? So we do not have to do anything. Okay. So this matrix is already in REF. So maybe for this one, I could have give you some more complicated questions, but I think we have time to work on at least one other question. Okay. So the matrix is indeed in REF. Only the final form is in REF. You can answer the questions. Okay. Now we determine if the given vectors U, V, and W are linearly dependent or independent. So anybody want to tell me the answer? Are they linearly dependent or independent? to answer that question, you check columns, right? You check columns. Is it true that every column has a leading one? The last column has no leading one, right? By that I mean not every column has a leading one. So the given three vectors u, v, and w are linearly dependent. So question? So they are, I mean u, v, and w are linearly dependent. Okay. After the answer to question A is no, I mean they are not linearly independent. If not, and then we have to write the second part of the question, so do not forget, okay? The second part is actually if a collection of vectors are linearly dependent, it's always possible to write at least one vector as a linear combination of two other vectors. We want to do that, okay? You just look at the final form. The end of the last class, I made some comments already. In the final form, you look at the last column, okay? If they're linearly dependent, then there's at least one column in the final form that can be written as a linear combination of two other columns. In this particular case, so maybe you try to write the answer in the chat, please. How to write W as a linear combination of U and V, so please. I was keep on running, I did not ask you any questions earlier, but this is kind of important. So please, just use U, V, and W. Now I'm looking for how to write W as a linear combination of U and V, so please. The second part of the question, okay? The second part of the question, so please, so try to tell me the answer, please. How to write W as a linear combination of U and V? W, the last column, is a linear combination of U and V. Okay, actually this number will give you the first coefficient. That number will give you the second scalar. I mean scalars. Okay. In this case we call them the scalars. So W can be written as a linear combination of U and V as, so now let's say 2 times U, right? And then plus 3 times V. Yeah, it's easy to verify that. Okay. Again, I want to repeat, if a set of vectors are linearly dependent, it's always possible to write at least one vector as a linear combination of two other vectors. Okay. And so basically I'm trying to connect the shortcut method to the definition, or the actual meaning of linearly dependent or independent. So we're done question A. Okay. Now we are going to answer question B. In question B, we are trying to determine if they span R3. They span R3. Okay. Probably I have enough room to answer question B on this slide. We move on to question B. Okay. We move on to question B. In question B, we are trying to determine if the given vectors they span R3 or not. We determine if the three vectors U, V, and W they span R3 or not. Now check our notes. We also have a shortcut method. Okay. We do the same thing. Can I use the matrix in here? I'll start over. Okay. We form a matrix with the components of U and V and W. in columns. Okay, you have 1 0 0, you have 0 1 0, so the first two columns. The third column is 2 2 3 0. Okay, again, this is a matrix in RIEF in row reduced echelon form, so this one is in RIEF. Okay, after putting a matrix into RIEF, then we can use the matrix in RIEF to answer question. Do they span R3? By that we mean is every vector in R3 a linear combination of the three vectors? Now let's recall the condition. So what do you check? We did that in the last class. You check the last row in particular. Okay, you check the last row. The condition is that the condition they do not span R3 is that there's at least one row consisting of all zeros. This is actually the case. So the answer to question B is no. By that we mean the given three vectors, they do not span R3. Okay. I just say they do not span R3, or more precisely, so we can say U, V, and W. This set consists of three vectors U, V, and W. They do not span. They do not span R3. You have to say they do not span what? Okay, they do not span R3. You look at the question. We're trying to determine if the vectors they span R3. Okay, they span R3. It means every vector in R3 is a linear combination of the three vectors. And then what we mean by they do not span R3, I'm going to answer the second part of the question. They do not span R3, it means not every vector is a linear combination of UV and W, right? I want to repeat. They do not span R3, it means not every vector is a linear combination of UV and W. By that we mean there's at least one vector in R3 that is not a linear combination of UV and W. Okay. This one is simple. So anybody want to tell me at least one vector in R3 that is not a linear combination of UV and W? Now we are going to find a particular vector that is not a linear combination of UV and W. Okay. To answer the second part of question B, we're going to verify. Okay, 001 is good. 001 is good. Actually, you have seen that. Okay, but for this part, so because we did not do any questions like that, okay, I'm going to show you a little bit more work on how to do this. Okay. In general, I think Karen has seen that, has told me already. Okay. In general, if you want to show at least one vector in R3 is not in the spanning set, it's not a linear combination of UV and W. In general, if the answer to question B is no, then at least one of the three vectors, you try to remember that at least one of the three vectors, 1 0 0, 0 1 0, 0 0 1. I mean at least one of ij and k will work. In this case, you guys just told me 0 0 1. Actually, the vector k will work. You have to show that. Okay, justify the answer. For the second part of the question, we claim the vector. So now let's say 0 0 1. The vector k, actually, right? 0 0 1. Can I use k to denote that? It's not a linear combination of UV and W. For this particular case, it's easy to guess. It's easy to check. But I will tell you how to show your work, how to do something in general. I'm trying to say if U, V, and W are more complicated, and then how to do things in, in general. Okay. Again, the first thing you want to check is probably 001. And then if K 001 so does not work, you could check I and J. Okay, I mean if K so does not work, you check 100, so which is I, right? And then you could check 010. It can be proved if the three vectors are not, if the three vectors they do not span R3, then at least to ij and k, at least one of ij and k will work. In this case, you'll see 001 will work. Okay. Okay, we want to claim this vector is not a linear combination of u, v, and w, right? So maybe to show that, to show the claim, we solve a equation of vectors. We solve a vector equation. Again, we want to determine if K is a linear combination of U, V, and W. Again, we want to determine if K is a linear combination of U, V, and W. So the corresponding vector equation is the following. Okay, the vector equation is going to be the following. We want to see if it's possible to write K as a linear combination of U, V, and W as a number times a number times U is actually I. Okay, a number times U, and then plus another number times V, and then plus another number, so now let's say Z times W, right? Again, K is a linear combination of U, V, and W. It means it's possible to get a solution to the equation. I mean, it's possible to get the three numbers x, y, and z satisfying the equation, right? So basically, to determine that, we need to see, we want to show that the equation has no solutions, right? Which means it's not possible to write K as a linear combination of U, V, and W. Again, we want to show the vector equation has no solutions. Okay. Now a little bit more thing. Okay, so this thing is converted to a linear system. We have seen that too many times already. Okay, now I'm going to write. I just gave you the augmented. Okay, so how about I will give you the system. The system corresponding to the vector equation is going to be the following. Okay, x times u. We compare the components. Okay, we have x plus 0y. I will include all the 0 components. Okay, so 0 times y, and then plus 2 times z is equal to 0. So do you know what I'm talking about? I'm converting the equation of vectors to a linear system. You compare the components. I'm jumping a little bit. I hope you can follow. Okay. And then the second equation is 0x, and then plus 1 times y, so which is y actually, and then plus 3 times z is equal to 0. And then the third equation is simple, right? The third equation is 0x, and then plus 0y, and then plus 0z is equal to anybody want to tell me the right hand side? If you can tell me the right hand side, then you'll see what's going on. Then I can tell you'll see what's going on. I just don't want to lose you. So please, anybody want to tell me the right hand side of the last equation? 1, it's 1, okay. Again, what I did is to convert the vector equation to a system of linear equations by comparing the components. I did jump a little bit, but I hope you can see what's going on. Okay. To solve the system, you write the augmented matrix, right? 1, 0, 2, 0, and 0, 1, 3, 0, and then the last row will give you. It's the last row is determined by equation 3, so which is 0, 0, 0, 1. The bar is here, right? At this point, actually the matrix is indeed in REF already. So this one is in REF already. But in the general case, you have to do some more work. Okay. If U, V, and W are a little bit more complicated, but this one is in final form. At this point, you can see the system has no solutions, right? So do you? Because the last row corresponds to an equation. This equation can never be satisfied. So that makes sense? The left hand side is 0, the right hand side is 1. Or you can use the condition under which a system has no solutions. Okay. There's a leading one to the right of the bar. That's the condition the system has no solutions. Okay. I'm trying to say the same thing in different ways. I give you many reasons. You just see one reason. Okay. It's sufficient. Which means this vector equation has no solutions, which means K is not a linear combination of U, V, and W. Okay. I will squeeze the last sentence in here. Okay. So that's why the vector K is not a linear combination of U, V, and W. Okay. Which means not all vectors in R3 is a linear combination of U, V, and W, right? Or U, V, and W cannot span R3, so that's more convincing. So that's how you answer question B. Okay. In question 3, we're trying to determine do they form a basis of R3? Remember the context. Okay. Do they form a basis of R3? I'm going to copy the question to the slide as well. I mean the 3 vectors. Again, the first vector is denoted by U, the second one is V, the third one is W. Okay. So question C is easy. So do they form a basis of R3? These are the 3 vectors in R3. Do they form a basis of R3? In order a set of vectors form a basis of R3, the 2 conditions. Now let's recall. So this time we treat R3 as the subspace of R3, a trivial one, right? Do they form a basis of R3? The 2 conditions are, in order to say they form a basis, you have to verify 2 conditions. They are linearly independent, and they span R3. None of the 2 conditions are satisfied, right? Let us say, okay, so the answer to question C is no. You just mention one of the 2 conditions is not satisfied. Okay. You say because I was trying to write because. So good enough. So because, okay, they are not. Again, you just mentioned at least one of the two conditions is not satisfied. Then the answer is no. Okay, so that makes sense. They are not linearly independent. Actually, we have seen u, v, and w are linearly dependent, right? By that we mean it's not possible. Okay, okay. So I do not want to make the thing too complicated. So the answer to C is no. So we are done question C. So be careful the wording. On Friday, I could give you a different set. Only if they do not form a basis, you proceed to question D, E, and F. In this case, the given three vectors, they do not form a basis of R3. So we proceed to D and F. Okay. Now we answer question D. Now we are going to determine the subspace spanned by the given vectors. I'm trying to determine how much space I need. Yeah, so that's the new slide. I duplicated. So I'm going to answer question D. Okay. So question D is relevant to one of the quiz questions we did on Friday. You remember the last question on your quiz? All the linear combinations of u, v, and w is from a subspace of R3. We proved that. Okay. And also, I think we did that last time. Okay. If you do not remember, I will go over some more details. Okay. Now for question D, we'll do question D right now. Okay. The subspace spanned by the three vectors u, v, and w is the set consisting of all the linear combinations of u, v, and w. Okay. In question 2, I mean in question D, so we just write that. Okay. Now in question D, as or the standard notation is actually the spanning set of u, v, and w. I'm going to write that. Okay. The definition. You write span. It means the spanning set of u, v, and w. The spanning set of u, v, and w. The definition of the spanning set is the set consisting of all the linear combinations of u, v, and w. Okay. It means the set consisting of all linear combinations of u, v, and w. You can use any coefficients you want. I mean, you can use any scalars you want. In this course, we call them scalars. Okay. You get all possible linear combinations. So now let's say a number times u, and then plus another number times v, and then plus a number c times w, and then you make a, b, and c run through all the real numbers. So last Friday we proved, so this one is indeed a subspace of R3, right? You remember I showed you how to verify this one is closed under the vector addition, and I told you to verify it's closed under scalar multiplication and including the zero vector, right? I believe you. We'll take that for granted. So this one, the definition. So that's how we define the subspace spanned by the given vectors. Okay, now we'll take that as the answer to question D. Okay. So how about we just check one of the particular vector to see if it's a vector in the spanning set or not. It's not part of the solution. I will try to understand the meaning of the spanning set. Okay. Now, for instance, if I give you a vector with 3 components, so now let's say 1, now let's say, okay, now let's say 5, 6, and 0. Now let me try again. Okay, if I give you a vector, so now let's say 5, 6, and 0. Is the vector in the spanning set of UV and W? All vectors in the spanning set is the set consisting of all linear combinations of UV and W. In order to see if that vector, you look at the mouse cursor, is in the spanning set, all we need is to answer, is that vector a linear combination of UV and W? If it is, how to write that vector as a linear combination of UV and W? This vector is a linear combination of UV and W as, okay, I will write UV and W. So please, does anybody want to tell me how to write the vector as a linear combination of UV and W? I think it's 5 times U and then plus 6 times V, right? You look at UV and W in question. And probably 0 times W. I'm trying to say that vector is a linear combination of UV and W. That's why that vector is in the spanning set. The spanning set consists of all the linear combinations of UV and W. So that makes sense now? That little question is designed to show you the meaning of the spanning set. The spanning set is actually it's called the subspace spanned by the given 3 vectors UV and W. Okay, so we're done question D. We'll move on to question E. Okay, we'll move on to question E. In question E, we are trying to get a basis of the spanning set. Actually, question E is kind of long. I will try to see if I can put everything on one slide. You look at question E, okay? I told you a question like that is trying to summarize all the things we have learned in past many classes. In question E, we are trying to get a basis of the subspace spanned by the 3 vectors UV and W. Okay. So before we do question E, anybody want to guess the dimension of the spanning set? The dimension of the subspace spanned by the 3 vectors UV and W? So just try to understand the meaning so geometrically. Actually, you have seen W is a linear combination of U and V. It's kind of saying W is redundant in order to form the spanning set. Okay, we'll do question E, then I'm going to make more comments. Okay. Okay, now for question E, we're trying to get a basis of the spanning set, the subspace. Okay. Again, you have seen W is a linear combination of U and V. It's kind of saying W is redundant to form the spanning set. You're going to see in more details. Okay. But if W is redundant, and then you claim U and V from a basis of the spanning set. Okay, we'll claim that again W is redundant. W is a linear combination of U and V. It's kind of W can be so determined by U and V. Okay, W is redundant. So in the basis you do not include W. So that's the idea. Okay, very shortly I will so we're going to prove that. Okay, we claim that we want to show U and V from a basis. Okay, the two vectors from a basis. Okay. Verify the two conditions. We want to show U and V from a basis. You have to do two things. U and V are linearly dependent, so that's one condition, right? The other condition is a little bit harder. We want to show every vector in the spanning set is a linear combination of U and V. Okay. So this time the first condition I want to verify is U and V are linearly independent. Okay. So to show that so this one is easy, right? You look at U and V, you put the components of U and V in columns. We use the shortcut method. Okay. In columns 1, 0, 0, so 0, 1, 0. The first column has components of U. The second column has the components of V. Right? It's already in RIF in row reduced echelon form. Okay. After seeing that, in general, you have to do something. You have to perform row operations to put the matrix into RIF. Okay. But this one is already in RIF. After see that, you say so U and V are linearly independent. Now you recall for a basis, so there are two conditions, right? Linearly independent, and then the second condition we have to verify is that every vector in the spanning set is a linear combination of U and V. Okay. So secondly, we choose any vector in the spanning set. So basically for each vector in the spanning set, each vector in that set is a linear combination of U, V, and W. We choose an arbitrary vector AU and then plus BV and then plus CW from the spanning set. We want to show each vector in the spanning set is a linear combination of U and V only. It's kind of saying W is redundant. We have AU and then plus BV and then plus CW. That's a vector in the spanning set, which means that's a linear combination of U, V, and W. Anybody want to tell me how to write that vector as a linear combination of U and V only? That's what we want, right? We want to show any vector in the spanning set is a linear combination of u and v only. Okay, it's AU, so there's nothing you can do about that. And then plus BV, right? So do you want to recall W is actually a linear combination of U and V? It's kind of W is redundant, right? Now we're going to rewrite W as C times W is 2U and plus 3V. You recall question 1. I'm trying to say in question A we have seen it's here. I think it's here. W is 2U and plus 3V, so we're going to use that. W is 2U and then plus 3V, right? Okay, now all we need is to write that as a number times U and then plus another number times V, right? By that we mean we write that as a linear combination of U and V only. Okay. Simplify a little bit. I think okay, I'm not going to jump too fast. Okay, I think it's AU plus BV and then plus 2CU. So do you see 2CU and then plus 3CV? Now we regroup, put U's together and then we put V together. Okay. By that we mean U A plus 2C, right? And the scalar before V, I believe, is 2C plus, sorry, B plus 3C. I think you know what's going on. So you put U's together, okay? You put two terms with the U together. You put two terms so with the V together, okay? And then you take out the number. It's permissible for because of distributivity. Okay. What I'm trying to do now? I just showed every vector in the spanning set is a linear combination of U and V only, right? What do we mean by that? So U and V span the spanning set. Okay, it's kind of saying W is redundant. So do you see we actually showed all the linear combinations of U, V, and W is actually all the same as all linear combinations of U and V only? It's W is redundant. It's kind of saying that, right? Okay, this set, the subspace can be spanned by two vectors only. W is redundant. Okay. Okay. Now you take a look at what we have proved. U and V are linearly independent, and also they span the spanning set, so they form a basis of the spanning set. Okay. I read so many sources, so can use thus now. Thus, they form a basis. The two vectors U and V form a basis of the spanning set. Now the spanning set is that's what we want, right? That's in the claim. We wanted that. We wanted to show U and V form a basis of the spanning set. Sorry, I should have written some of the spanning set of U of U, V, and W. I mean span. I know it's a little bit long, but I hope you can follow. I hope it's not too hard to follow. I hope everything makes sense to you. So we're done question E. Okay. One more question, and then we're done. Okay. Determine the dimension of the spanning set. For this one, I'm going to use the standard notation. Okay, the dimension of the spanning set of U, V, and W. Anybody want to tell me the dimension right now? Dimension, please. What is the dimension of the spanning set? The dimension is how many, you count how many basis vectors, right? So that's no, actually that's 2, right? We just proved 2 vectors from a basis of the spanning set. I think we had a typo. So the dimension is 2. Okay. So because 2 vectors from a basis, okay. Actually the spanning set is not the entire R3. The dimension is 2. Okay. So we just did that. We're going to answer the same set of questions for these 3 vectors. So this one is easy. Okay. You put the components in columns 1, 2, 1, 2, 1, 0, 0, 0, 1. And then we perform row operations. The final form is 1, 0, 0, 0, 1, 0. Okay, 0, 0, 1. Again, now we're trying to answer all the questions. Are the vectors linearly independent? I'm trying to answer all the questions. Okay. You just remember the final form is identity matrix. Okay. Now we're trying to answer all questions. You look at question A. Okay. Are the vectors linearly independent? Every column has a leading 1. Then the answer to A is yes. Okay. If the answer to that part is yes, you do not have to answer the second part. And then determine if they span R3. No rows consisting of zeros. The answer to that is yes. So you do not have to answer the second part of the question. Determine whether they form a basis of R3. Do they form a basis of R3? They're linearly independent, and also they form a basis, right? And also they span R3, so they form a basis. Okay. If the answer to A, B, and C are yes, then you do not have to answer D and F.